Space has a simple rule. It tries to kill you. It does not care if you are ready. It does not care if you are brave. It only cares about pressure. On Earth, air pushes against your skin. You don't feel it, but it's there. In space, that push is gone. Zero. If you stepped outside without protection, the air inside your lungs would rush out. The water in your body would boil. It is a brutal, instant physical wall. For decades, the only way to beat that wall was to dress like a tank. You have seen the pictures. Big, white, puffy suits. They looked stiff because they were stiff. Moving in them was a fight. Bending an arm took real strength. Working for 6 hours left astronauts bruised and exhausted. That physical limit killed speed. It killed budgets. It made space travel feel like a rare, heavy event. SpaceX looked at that same wall and saw a different problem. They didn't just need a suit that worked. They needed a suit that could be built fast. They needed a suit that fit perfectly every time. And they needed a suit that didn't cost $20 million a pop. So they built a shop. This is the part most people miss. They expect a white laboratory with robots. They expect guys in clean suits holding clipboards. If you walk into the SpaceX suit lab in Hawthorne, California, that is not what you see. You see tables, you see fabric rolls, you see sewing machines. It looks like a fabrication shop. It looks like a place where people make things with their hands. That visual tells you everything about how they solved the impossible problem. They turned a science project into a manufacturing job. They brought the work in-house. They put the suit team right next to the rocket team, and they started cutting cloth. A spacesuit sounds like a high-tech machine. It is. But it starts as a pattern on a table. The constraint is brutal. The suit has to do 4 things at once. It has to hold air in, it has to keep heat in, it has to stop fire, and it has to stop tiny space debris from tearing a hole. If you miss one, the suit fails. If the suit fails, the mission ends. Most companies tried to solve this with one thick layer. It feels safe. Thick means strong, right? But in space, thick means stiff. A thick layer balloons out under pressure. It turns the astronaut into a statue. SpaceX went the other way. They built a stack. The suit is made of 14 different layers. That is a specific number, 14. Each layer has a single job. Think of a winter coat. It keeps you warm. Now imagine a coat that has to hold a vacuum, reflect the sun, and stop a bullet. You can't buy that fabric at the store. The shelf in the Hawthorne lab is full of specific roles. The first job is holding shape. When air pumps into the suit, it wants to expand. It wants to turn into a circle. The suit has to fight that shape. SpaceX uses a restraint layer made of nylon and materials coated with Teflon. These layers are tough. They don't stretch. They cage the pressure. They force the air to hold the shape of a human, not a balloon. Then comes the cold. Space in the shade is about minus 250 degrees Celsius. That is not just cold. That is a temperature where metal gets brittle. A home freezer is minus 18. The gap is massive. To fight that, they use aluminized mylar. It looks like foil. It reflects heat back to the body. They mix it with a mesh material called Dacron. The mesh creates tiny air gaps. Those gaps trap heat. It is a system. The foil reflects. The mesh traps. The cold stays out. Then there is fire. Inside a spacecraft, fire is the worst-case scenario. You cannot run away. So the outer layers are built to resist flame. They use materials like Kevlar and Nomex. These are fibers that don't burn. They char. They protect the layers underneath. And finally, the stack itself protects against debris. If a tiny rock hits the suit, the top layer might tear. But the next layer catches it, and the next. The stack spreads the energy. It stops a cut from becoming a rip. This is technical mastery. It is not about inventing a magic cloth. It is about choosing the right 14 layers and sewing them in the right order. And that is where the sewing machines come in. You can see them in the footage. Heavy-duty industrial machines, the kind you see in a car factory or a sail loft, they are made to push needles through heavy stacks of cloth all day long. This matters because of the seams. A seam is a hole you make on purpose. You poke a needle through the layer that is supposed to hold air. That sounds crazy, but if you stitch it right, the thread fills the hole. The tension pulls the layers tight. The seam becomes as strong as the cloth. Doing that with 14 layers is hard. If the tension is off, the fabric puckers. If it puckers, it leaks. If it leaks, you have to rip it out and start over. That is why the people in the lab are not just engineers. They are craftsmen. They are tailors who understand load paths. They know how to curve a seam so it doesn't rub the astronaut's shoulder. They know how to finish a joint so it bends without binding. That is hand skills applied to life support. But even a perfect stack of fabric is useless if it doesn't fit. This is the second big failure of the old days. Old suits came in sizes: small, medium, large, maybe extra large. That works for buying a shirt. It does not work for space. If a suit is 2 inches too long, the knee joint sits on your shin. When you try to bend your leg, the suit fights you. Under pressure, that fight becomes a workout. Astronauts in the old days would come home with bruises. Their fingernails would fall off because the gloves pressed so hard against their hands. SpaceX decided to fix the fit before they sewed a single stitch. They made the suit custom. Every astronaut who flies on Crew Dragon gets a suit made for them, not adjusted for them, made for them. The process starts with a tape measure. It looks old school. A technician measures the arm length, the chest, the waist, the distance from hip to knee. They map the body, then they cut the pattern. They use the measurements to shape the 14 layers. They build a prototype. Then they put it on the astronaut. They ask them to move, reach for a switch, turn your head. They look for the pinch points. If the shoulder is tight, they mark it. If the elbow is loose, they pin it. Then they go back to the table. They adjust the pattern. They sew it again. This is a loop: measure, build, test, fix, measure, build, test, fix. It takes time, but it buys performance. A custom suit means the joints line up with the body's joints. When the astronaut bends an elbow, the suit bends right there. No fighting, no bruises. It means they can sit in the capsule for hours without pain. It means they can focus on the mission, not on a rubbing seam. Comfort is not a luxury here. Comfort is safety. A distracted pilot makes mistakes. A comfortable pilot stays sharp. This brings us to the helmet. The helmet is the crown jewel of the suit. It has to seal around the neck. It has to provide air. It has to hold a microphone. And it has to protect the head. In the past, helmets were made in molds. You poured plastic into a shape. You waited for it to cure. Then you pulled it out. If the shape was wrong, you had to make a new mold. That took weeks. It cost thousands of dollars. SpaceX skipped the molds. They bought 3D printers. Inside the Hawthorne lab, you can see them running. They print parts out of high-strength plastic. They print the valves. They print the visor locks. They print the cooling ducts. And they print the helmet structure itself. This changed the game. If a helmet didn't fit right during a test, they didn't have to wait for a new mold. They just changed the file on the computer. They hit print. The next morning they had a new part. That is speed. That is how you solve problems in days instead of months. It also let them do something else. They could build the helmet to match the head. Everyone has a different head shape. Some are rounder, some are longer. A standard helmet leaves gaps. Gaps need padding. Padding creates hot spots. The SpaceX helmet is printed to fit. It sits stable. It doesn't wobble when the rocket shakes. It also integrates the systems. The microphone is built in. The air valves are built in. The visor mechanism is built in. And here is the kicker. The visor handles the touch screens. Crew Dragon is flown by touch screens like a big phone. The glove has to work on the screen. The visor has to be clear enough to see fine details. The lab tested this over and over. They found that if the visor was too far from the face, it was hard to see the edges of the screens. So they printed new shapes. They brought the glass closer. They cleared the view. They did that in-house. No vendors, no contracts. Just print and test. Now, there is a rumor you might have heard. People see this clean white lab and they ask about the vacuum chamber. They assume SpaceX has a giant steel room hidden in the back where they test these suits in a vacuum. A secret chamber. The truth is more practical. SpaceX does not have a secret chamber in Hawthorne. They don't need one. Building a vacuum chamber is expensive. Running it is dangerous. You need huge pumps. You need safety teams. You need massive power. But NASA already has those chambers. They built them in the 1960s for Apollo. They are sitting in Houston at the Johnson Space Center, so SpaceX uses those. They build the suits in Hawthorne, they fit them in Hawthorne, then they ship them to Houston. They put the suit in the NASA chamber, they suck the air out. They test it for real. This is smart business. Why build a duplicate lab when you can use the best one in the world? It also proves the suit is real. Passing a NASA chamber test is the gold standard. It means the suit is not just a costume. It is a certified life support system. The Polaris Dawn crew used those same chambers to test their EVA suits. EVA means extravehicular activity. That is a spacewalk suit. That is a harder job. An EVA suit has to work outside the ship. It has to handle direct sunlight and direct shadow. It has to protect against radiation. SpaceX used the Hawthorne lab to build those too. They used the same team, the same machines. They just added more capability to the stack. Then they proved it in Houston. This split approach, build local, test global, is how they move so fast. They focus their money on the sewing and the printing. They use partners for the heavy testing. This leads to the biggest question. How much does it cost? A standard NASA EVA suit costs millions. Some estimates say between $12 and $25 million for one suit. That price comes from complexity. The NASA suit is a spaceship. It is a backpack called a PLSS. That backpack has its own oxygen tanks, its own scrubbers to clean the air, its own batteries, its own radio. It is fully independent. You could float away from the station and stay alive. That independence is heavy. It requires thousands of parts. Each part has to be tested. That drives the cost to the moon. SpaceX made a different choice for Crew Dragon. Their suit is an IVA suit inside the vehicle. It does not have a backpack. Instead, it has a tether, a specialized cord that plugs into the seat. The spacecraft provides the oxygen. The spacecraft provides the cooling. The spacecraft provides the power. The suit just has to distribute it. By moving the heavy machinery into the ship, the suit becomes lighter, it becomes simpler, it becomes cheaper. It is a fraction of the cost of an EVA suit, not because it is cheap quality, but because it has a focused job. It is like the difference between a work truck and a daily driver. The truck has to carry heavy loads and go off-road. It costs more. The daily driver just has to get you to work safely. It costs less. SpaceX built the daily driver for space, and because it is cheaper, they can make more of them. This is the hidden power of the lab. If you have to pay $20 million for a suit, you treat it like a jewel. You reuse it for years. You are scared to change it. If you can build a suit for a fraction of that, you can build a new one for every mission. SpaceX builds a fresh suit for every astronaut. That means the fit is always perfect. It means the materials are always new. No wear and tear from the last guy. It also means they can upgrade the design. If a pilot says the glove feels stiff, the team changes the pattern. The next suit that rolls off the line has the better glove. They don't have to wait 5 years for a new model. They iterate. This is the same way they build rockets. Fly, learn, fix, fly again. Most government programs get stuck in design. They spend years arguing about the perfect zipper. They write reports. They hold meetings. SpaceX just sews the zipper and tries it. If it jams, they cut it out and sew a different one. That mindset is why they are winning. They value the result more than the process, and the result is flight. Today, Crew Dragon flies regular missions to the space station. Private crews are flying higher than ever before. Every one of them is wearing a suit made in that shop in Hawthorne. The suit connects to the seat. The seat connects to the ship. The ship connects to the rocket. It is one integrated machine. When you see the astronauts walk out to the Tesla, they look cool. The suits are sleek. They are black and white. They look like the future. But don't let the look fool you. The style is just the wrapper. Underneath the white fabric is the nylon restraint layer holding back the pressure. Under that is the mylar reflecting the cold. Under that is the Nomex fighting the fire. And underneath it all is a pattern cut by a human hand to fit a human body. That is the magic. It is not high-tech wizardry, it is craft. It is taking a deadly environment and stitching together a solution one layer at a time. This matters because we are going further. We are going back to the moon. We are aiming for Mars. Those trips are long. They are dangerous. The suits will have to get better. They will have to handle dust. They will have to handle months of wear. The lab in Hawthorne is already working on that. The EVA suit for Polaris Dawn was the first step. It showed they can step outside the ship. They used the same team, the same printers, the same sewing machines. They just solved a harder problem. That is the trajectory. Start with the inside suit. Master the fit. Master the production. Then step outside. Then step onto the surface. The giants of the past built amazing things, but they built them slowly, and they built them at a price that couldn't last. SpaceX is proving you can build safety at speed, you can build performance at scale, and you can do it with a sewing machine. The next time you watch a launch, look at the crew, look at the gloves, look at the helmets. You are not looking at a costume, you are looking at a system built to keep the soft, fragile human body alive in the hardest place there is. It works because they respected the physics. It works because they respected the fit. And it works because they weren't afraid to do the work themselves. The gap between the old way and the new way isn't just money, it's mindset. One treats space like a rare event. The other treats it like a job. And when space becomes a job, with tools that fit and gear that works, that is when we actually get to stay.